My name is Raphael Cassia. I'm the chair of the Audio Engineering Society's South German section, and it is my great pleasure to welcome you all to this event. If you are interested in joining the AES, joining the section events, or being notified about upcoming events, then please see the links and QR codes you can see on screen, or just get in touch with any one of us. So without further ado, I will invite Elena Shavalina, who is in charge of organizing the colloquia, to say a few words and introduce our speaker. Thank you.
Thank you very much, Raphael, and hello everyone. It's nice to see so many of you here from all over the world. And today our topic is room acoustic analysis with a sound particle diffraction method. This presentation is by Thomas Schütt from SoundPLAN, which is actually in South Germany, located in Backnang, very close to DMB, so we're basically neighbors. And Thomas is a software developer at SoundPLAN, specializing in indoor noise and room acoustics. He obtained his master's and PhD from the University of Nottingham in the UK with a research focus on ultra-cold atoms. He subsequently lectured in computational quantum physics at the University of Tübingen in Germany before joining SoundPLAN in 2015. Tom, thank you very much for being here, and the stage is yours.
Thank you very much. Just wanted to say how pleased I am to be here, and very pleased to receive a suggestion from Elena that I do one of these colloquia, because my experiences have had some really productive discussions in the past with the audio engineering community. I guess that's because we're sort of similar but different in a way. Obviously, we're all concerned with sound, but I sometimes joke that the audio engineers kind of have the fun side of the business, crafting sound to put a smile on people's faces, whereas at SoundPLAN, we're more sort of the complaints department, so to speak. Well, our line of business is making software for noise control and acoustics. So we're often worrying about, okay, is it too loud here? Are these reverb times in line with what this building needs to be for this particular purpose? How's the speech intelligibility stuff? So we're more in the business of removing frowns, perhaps, than making smiles. Nonetheless, we're all in the sound business, and so I find we have a lot of useful stuff to talk about. I'm hoping for some good exchanges here. In the past, I've enjoyed talking maths and acoustics with Elena. She's actually one of the very few people I know who genuinely enjoys discussing mathematics for fun. But yeah, the acoustics have proved very productive. As you said, we're actually in the same sort of medium small town, and we've done a bit of cooperation together in the past, and that's a good thing. So I thought, well, the chance to talk to even more acoustic engineers can't be a bad thing. So I'll begin hopefully by sharing my screen. A sort of core feature of this presentation will be about the sound particle diffraction method. This was a new method for doing room acoustics based on sound particle ray tracing style methods that we introduced about 5 years ago into the market after a collaboration with some researchers at a university. In that time, it's I think I can say it's done well, but also we've encountered some various challenges and interesting topics that have come up in the 5 years since we've had it out in the field. And I thought I'd like to tell you a bit about some of those topics, which hopefully will be of mutual interest. In fact, I think it's rather a good thing we've got a longer format today. The way I've structured this presentation is it's rather different from how I would do it if I were talking to our customers. So I'm hoping I'll put some topics on there where we can have a bit of back and forth and exchange some ideas. So in a bit more detail in terms of structure and content, I'll start by giving you a bit of background on how we came to get into the sound particle business. I always think it's easier to understand stuff if you know what it's for and what sort of problems it's trying to solve. So I'll explain sort of where it comes from, so to speak, before going on to describe the method with a few animations, so hopefully give you an idea of what's going on under the bonnet and why it is the way it is. A bit of emphasis I'll place on diffraction, because that was kind of the big thing of this method. It's been a long-standing problem in room acoustics, how to handle diffraction in a way that's both feasible and yet sort of reasonably realistic, and we like to think we made a bit of progress with that one, so I'll tell you about what we did there. And having got the method explained, I'll go on to sort of talk about this method in practice and some issues which I think may be relevant for us when you go about doing some room acoustic modeling. A particular issue is the trouble of scattering of the sound field. This is a thorny issue if you're in this kind of business, and I'd like to show you the kind of trouble it can cause and what one might deal, well, how one might go about dealing with it. And this will bring us to a discussion of a level of geometrical detail one might consider appropriate when doing these kind of models. And of course, that goes hand in hand with a topic very close to my heart, uncertainty analysis. So I'll look at the kind of plus minuses one expects in these fields and how they affect how we go about working with these methods. And that will all feed into a slightly facetious question, shall I say, because this does come up from time to time. The question is, if you're modeling some sort of acoustic space, do you need to do the chairs? Well, I promise you answers before this presentation is ended. And having looked at a bit of practical stuff with the sound particle method, I thought, just for the sake of generating a bit of discussion, I'd do some sort of slightly more exotic and futuristic topics. Our approach to oralization, this is perhaps the nearest we come to acoustic engineering. And furthermore, I sort of sell this with a slightly silly headline, the idea of processing your sound on the graphics card. In reality, it's a little bit more mundane than that. You may have heard of using hardware acceleration techniques using the graphics cards to make your simulations run faster. I'll share some of our experiences with that. And finally, very futuristic, the idea of taking these sound particles outdoors. We're not the only people doing this sort of method, but pretty much everybody has them exclusively as a kind of indoor method. Nevertheless, there's potential to take them outdoors. Let's say you're doing an outdoor concert or something. The trouble is you do have to think about some of the extra physics which occurs outdoors. And I'll bat some ideas around there. Incidentally, if you're having a bit of trouble with my audio quality, I humbly apologize. I literally sat down with a professional A&R guy earlier this year and went through all my Zoom settings. And I even asked him specifically if the audio was okay without any external equipment. He said it was absolutely fine. So my deepest apologies, the best laid plans and all that. But anyway, let's crack on, all being well. So I hope that slide's come up for you. The reason I ask is I'm not seeing the usual border around the thing, but if everyone's got a slide with an envelope on it and a title about wave physics, then I'm happy. So I talked about sound particle methods. It is a geometrical acoustic method. As such, it's a bit like you have rays of light which just move in straight lines, hence we say it's akin to ray tracing. But of course, when you do ray tracing of light and tracing these light paths, or sound paths in this case, you have effectively ditched wave physics when you do that. And in the process, you ditch important things like diffraction when you do that. So, well, why don't we use wave physics? Or why can't we do that? Well, You've heard of back of envelope calculations. I literally did do this one on the back of an envelope. And the thing I was interested in was to say, if I have a computer with 8 gig of RAM, what's the largest volume I can simulate and still hope for half sensible accuracy? And so I was looking in this specific case of the finite difference time domain method, the FDTD, which some of you may have heard of. And I sort of said, okay, well, let's go up to 4,000 hertz, see what we can do. And the result of this was, I reckon my estimate is I can do a cube with a side of 27 meters. If you're doing room acoustics and say you're doing speech intelligibility and you want the 8 kilohertz band as well, then of course that halves down to 13.5 meters. So these numbers are not stupid, but they are tough. So even for a sort of moderate sized open plan office, you've maxed out your computer's resources, and we haven't even started talking about the run times yet, and they are quite painful. And so at the moment, it's not quite feasible to sort of talk about a product which does full wave physics. Discussions are ongoing, of course. This is one occasion where nature is a little bit kind to us, because the worst of the wave physics, the stuff where it really deviates from other methods, is at the low frequencies. And of course, the low frequencies are easier to do with these methods. So the discussion's ongoing. You've got to be a bit careful with how you simplify your geometry and stuff. So it's not going to be easy. But yeah, that's something people are thinking about. But as things stand, if you want to do a room acoustic product, you'll find it hard with wave physics. Hence, we go for these geometrical sort of ray tracing-like methods. So back in the day, when people first started getting into these noise propagation things in the noise control arena, both outside and inside, you needed fairly simple recipes to do it. SoundPLAN was founded back in 1986. We had a DOS version back then. Occasionally, I still see little bits of evidence of DOS days in the code, which is always quite amusing. But obviously, we're on more modern platforms these days. And in the course of the 90s, we began doing things like factories and noise and industrial buildings and the like. And the way you tend to handle the stuff in the noise control industry to a first approximation is you use the mirror source method. And the way this works is, if hopefully you can see the red source there and the white receiver. And of course, you make a link between those two and you say, okay, well, there's the direct sound. Let's calculate the contribution. But of course, we've got reflections to worry about too, say from boxes or machines or buildings. And so you need to calculate those things. And the way you do it is you assume that the surfaces you're reflecting from, the planes in which they sit, effectively act as mirrors. And from that, you get these mirror sources in which the original source is effectively mirrored in that surface. And this gives you some new straight lines so you can calculate. They're a bit longer, obviously, because the paths are longer. And you throw in the absorption and you're happy. And this works really, really well for a limited number of reflection orders. The trouble is that as you increase the reflection order, if you do it naively, you see an exponential increase in the number of these mirror sources, because with every new reflection order, all the previous mirror sources have to be reflected in all your surfaces, and they kind of multiply and breed like rabbits. So if you're in an indoor environment where potentially you could have dozens of relevant reflections, this starts to get a bit too painful. So over the years, people are saying, okay, well, perhaps we need to update these methods and look a bit more at what the concert hall guys are doing with these rays. And so this brings us to the sound particle method. There are some people who get quite pedantic about this and say there's a difference between sound particles and ray tracing. To be honest, I view them as being pretty much the same. There are sort of little details in this, but just think of them as rays, or you can think of them as chucking a load of bouncy balls around a room. We have our particle cannon there. I hope the animation's working for you. And this particle cannon shoots out particles in all sorts of funny directions. And over time, these things bounce around and you get a distribution. This actually did happen in my house once when my wife bought the kids a bag of bouncy balls, and being kids, they didn't content themselves with just chucking one ball around. They chucked the whole lot simultaneously, and it did look rather like this. So that's the kind of picture to have in your head for the sound particle method. There are a number of physical processes which get incorporated in this. If I were talking to our customers, I would leave the maths out. So I hope you regard it as a compliment that I put the maths in for you. The classic process is, of course, for ray tracing specular reflection, or occasionally when I mispronounce it, spectacular reflection. This is as you would expect. The particle just hits the wall and comes out at the angle you would expect it to. However, there are a number of other things we need to consider. There is also diffuse reflection, and actually this is of great importance, as we will see later. This is a kind of reflection where the ball hits the wall but comes back at an unusual angle, possibly due to some sort of roughness on the surface, and diffuse effects are all around in acoustics, of course, and we need to make sure that we're covering them properly. Important to note, we do this with random numbers, and you will find actually there are a lot of random numbers in these simulations, which gives you a so-called statistical method where the results slightly fluctuate with repeated runs, but always within hopefully a fairly narrow tolerance band. So there's room scattering. This is what people used to do back in the days when you had to model a factory full of all sorts of machines, but there was no way you could model that kind of complexity. So what you'd do is you'd say, okay, I'm just going to set an average density of objects in the room, and that gives me a mean free path length for my particle. So at some point he flies through the room and just says, oh, I must have hit an object by now, I'm going to change my direction and maybe lose some energy in the process. So that's room scattering, quite an efficient way of doing rooms full of stuff. Transmission is also possible. You can do room to room with this method. This thing could, I guess, do some further research, and we're working on it a bit ourselves, because the way it's done is you'll fire a particle at the wall. Some will reflect, but there's a certain probability that some will go through. Of course, if you've got a very thick wall with heavy transmission losses, then that probability is pretty small. Hence, it can be quite hard to get signal to the other side. So we're working on some approximations that should come out in the next version. But yes, you need to keep an eye on that. Nevertheless, it is possible. And detection is something I would highlight, because this is a fundamental difference between the sound particle method and the previous mirror source thing, in which the receivers were points and you would make explicit links between the sources and the receivers. In the case of the sound particle method, there is no explicit link. The particles just wander kind of aimlessly around the environment, reflecting from things. And if they happen to bump into a receiver, they happen to bump into a receiver. Of course, you want that. But it does mean that if your receiver is difficult to find, if it's hidden away somewhere or it's very far away, it's going to take the particles a while. So this does affect the efficiency. The receiver has this finite spatial extent. And obviously, the bigger you make it, the more particles you can collect more rapidly at the cost of some spatial resolution. So the particle flies through, we get the crossing length, and we get the energy dump that we need just there. So that's all very well, and that was how these kind of ray tracing methods for sound worked for many, many years. And a long-standing problem was that of diffraction. In fact, in the very year SoundPLAN was founded, 1986, one Professor Uwe Stephenson, he's now retired, but he used to head up a group at the Hafen City University in Hamburg. He was worrying about how you could get diffraction back into these methods in a realistic way. As I said, having ditched wave physics, diffraction has to be shoehorned back in, so to speak, with various levels of approximation. So how do we go about doing this? Well, what have we done in the past? Well, the mirror source method, implemented according to the ISO 9613, which us noise control people know and love very much, is the so-called detour method. It's also known affectionately as the rubber band method. And diffraction, according to this scheme, works as such. So source in red, receiver in blue, and you imagine you stretch a rubber band between these two, and any obstacles between them sort of push that rubber band slightly to the side, so effectively the rubber band goes tightly around any of those obstacles. The length of the rubber band increases, giving you the so-called detour length. And having got that detour around the objects, you then use some simple formulas to work out your diffraction. So this worked well to a first approximation. It should be remembered that the formulas were different for single and multiple diffraction, which could occasionally lead to some funny results going on, but it worked better than nothing, and that's what people went for. But the trouble is with these sound particles is detour methods do not work here. Sure, there's a path that goes tightly around the wall, but sound particles don't just stick tightly to walls, they go everywhere. So what are we to do about these extra particles? So there was this question, well, first, so we've got to find something that works for sound particles in the first place. And secondly, there was this question, well, can we actually do better than these detour methods, which are a bit rough and ready? And so we got chatting with, as I said, Professor Uwe Stephenson about this, and we ended up applying for one of those kind of university industry grants. And this was a story which had quite a happy ending. Doesn't always, but this was university research, which after about 3 decades finally got turned into a useful product. And the name of the method is so-called uncertainty-based diffraction. This is because I wouldn't claim the mathematics is the same, but there is an analogy with the Heisenberg uncertainty principle, and sort of that name kind of stuck. And the way it works is, say I've got my sound particle that goes whizzing past my little corner there. What I do is I've got my screening wall here, and I imagine I extend that screening wall with something called a virtual wall, which is acoustically transparent, and then I can note the point that my particle hits that virtual wall, and from that strike point I can get the distance between any solid objects I have close by. From these distances, these bypass distances as we call them, I can get an effective slit width, and of course a slit is integral to the idea of diffraction. So we'll call that B, our effective slit width, and then we plug that into the following formula. I know it looks ugly. I mean, for us, we consider that sort of fairly non-ugly compared with some of the other stuff we considered at the time. It's derived from Fraunhofer diffraction, but I must stress that this is mainly empirical. It's best to think of it that way, because normally the conditions for Fraunhofer diffraction don't really apply. Nevertheless, it sort of provides a sort of theoretical anchor point. But as I said, really the main goal is to just get something that's better than detour methods and closer to wave physics. And in various past papers, we've proved that it has. Anyway, if you use this kind of Fraunhofer derived formula, it's numerically quite friendly for you. You can pull some tricks. So that's the formula as it is there. And again, we've got random numbers here, and it tells us through which angle our particle should bend as it goes past the wall. And of course, it's a weighted probability distribution. For every case, the most likely direction for the particle is just to go straight on, but there is a probability it will get scattered into the wings. And that probability is determined by this effective slit width. It's also related to the wavelength that the particle represents as it flies by. So just a quick summary of everything that's in that method. So the classic ray tracing would involve emission, detection, specular reflection, possibly diffuse reflection as well. Bits, perhaps more modern additions, are the transmission, the room scattering, and most modern of all, the diffraction going in there. One thing, and perhaps I should say that is we quite like about the method is there are various diffraction schemes out there for these kind of methods. Some of them just try and take sort of the early sound into account, maybe the first one or two sort of diffraction events. But the way this works is you can just leave the diffraction on for the entire duration of your simulation. And so you end up with a kind of true physics engine. It means that at any point in the simulation, at any place, the rules are always the same. So that does help you avoid some unwelcome surprises. So you may be thinking, well, how much difference does all this make if you're in, say, some kind of concrete factory? And sure, you've got screening walls and the like, but you've got an awful lot of reflected sound. So you may be thinking, well, does it really matter very much? Because you can easily get around a wall with a reflected sound, assuming the walls are there. And that's probably make a bigger contribution than diffraction. This is true to a very great extent, as we'll be seeing in a couple of slides' time. But the funny thing is diffraction has some other weird effects, which are very important for room acoustics. And I'd just like to demonstrate how extreme that can get with an example here. You don't need to worry. It's normally not that bad if you're in the acoustic modeling business. I've deliberately designed this example to scare the hell out of people. But so it's normally not quite as severe, but it does show the difference it can make. And all I have here is just a simple hall. It's got some concrete walls and floor, acoustically hard. It's got an absorbing ceiling that absorbs pretty much everything. And I've got these acoustic panels on the wall, which are also absorbing. And note that these are 3D panels. They've got a certain profile. They stick out a few centimeters from the wall. And in doing so, they provide some kind of diffraction edges. So let's set this up and see what the reverb times look like. Now, if I do this without diffraction for 125 Hertz, I get a very long reverberation time, T60, indeed, of over 20 seconds. If I now turn my diffraction on, that reverb time is in a completely different area, just over 1 second. And it's a kind of crazy result, I know, possibly a source of worry. So let's try and understand what's going on. Well, it's the difference between low and high scattering. Don't forget there's an acoustic ceiling there. And if we don't have any mechanism to scatter those sound particles, what can happen is you get these kind of modes. In this case, it's a two-dimensional sort of structure in the sound field. So a particle goes off horizontally, and because it's only hitting concrete, it just goes round and round and round without ever seeing any of these absorbing surfaces. And as such, that's a long-lived mode, and it creates this enormous reverberation time. If, however, you do have scattering mechanisms, so some kind of diffraction at those corners, it will deflect the particles from out of its horizontal mode into trajectories with a strong vertical component. And then very quickly, either directly or after a single bounce on the floor, the particle sees that ceiling and is instantly absorbed, having an enormous effect on the reverberation time in the process. So these scattering mechanisms, as we see, are quite the issue. So perhaps that's kind of the picture to have in your head. I've just drawn a few particle parts for you there. In low scattering, you get this kind of two-dimensional sheet. You can also have a one-dimensional sheet, well, not a sheet, but a line of just things knocking back and forth between two parallel walls like that. So there's a lot of structure. In the case of high scattering, basically knocking things into trajectories with vertical modes gives you a completely different picture and destroys that 2D mode. This is a difficult issue because there are situations where you might end up with these kind of modes. For example, if you've ever encountered a whispering gallery in a church or something, it's not impossible you'll see such effects there. But in general, with these kind of methods and softwares, it's easy to create something that's a bit too symmetrical without the kind of normal mixing processes you would see in reality. And the result is you're more likely to create these kind of funny effects in the simulation. In fact, you'll if you can go around other people who do these kind of methods, and often their FAQs have warnings to be careful for this sort of thing. So we're not the only ones who've spotted this. So reverberation times look troublesome, as you can see. How are other acoustic parameters affected by scattering? Well, as I mentioned earlier, if you were questioning whether diffraction makes much difference to the sound level in an acoustically hard room, as I say, answer not very much, quite frankly. I mean, in comparison with that reverberation time change, the sound levels drop by a couple of dB, so you'd notice it just about, but nothing dramatic there. The speech intelligibility, put diffraction on, that goes up by about maybe a third or something. The D50 definition parameter goes up by about 50%. Likewise, the clarity, which is more or less the same thing, goes up a bit, but perhaps not quite as extreme as might be the case. The center time CT, that's unsurprising. That does change a lot because you've got this great massive late sound without diffraction, which disappears when you put the diffraction on. And the sound strength, again, that's fairly robust against this scattering effect. The lateral energy is more or less unchanged. So it's kind of interesting because it used to be the case back in the day that sort of reverberation times were the central kind of pillar of room acoustics and all the kind of norms and standards that we work with. You see increasing talk of other parameters these days. For example, for open plan offices, the ISO 33823 doesn't actually make use of reverberation times. It goes all the way with STI. And the conferences I've been to recently, more and more talk of D50 and G, which is a bit more robust against this kind of scattering effect. So how are we to best deal with these kind of issues of our sound fields when doing geometrical acoustics? This is something I tell to the guys who come and do our teaching seminars. Perhaps my number one weapon to combat this is iterative modeling, as it's called. Just to give you an example, I kind of dreamt up a slightly crazy architectural office here. The main thing is I didn't want too many sort of box-like surfaces. I wanted a range of surfaces, including curves and the like. And in its full case, I've kind of overmodeled it a bit. I mean, I've got these cylindrical pillars kicking around. I've got some even desk legs, the like, which normally you would never do, but I'm here to make a point here. So we've got all sorts of things. We've got drawers and chairs and tabletops and the like. And the question is, how do we go about doing acoustic modeling of this situation in an efficient way? So what I normally say to people is, top tip, try to avoid the situation where you take your architect plan, you put everything into your model, and only then, having put every last detail in, we've got this beautiful looking thing, do you start your simulation? That can lead to trouble. My advice is to start really, really simple, an unfurnished room. In this case, I've just got the walls and the partition walls here. And having done that, you wind your simulation up and you let it run and you see what the parameters are doing. So reverb times, speech intelligibility levels, that sort of thing. And having done that and got your reference, you then think about, okay, what are the most acoustically relevant objects, typically judged on the basis of equivalent absorption area. And so let's put those in, and then we rerun and see what effect that had on the room acoustic parameters, and see how much they've changed. And then you can go to the next level, add a bit more detail. Again, it's not exact science picking the order you stick things in, but just a bit of gut feeling usually works out quite well. And you run again, see how much the parameters change. And so you keep adding detail and checking parameters until you gain an idea for what the situation is doing. And our experience is, if you do that normally, the following happens. Here I've got 7 levels of complexity. So I started off with just the bare room, then I added the think tanks, those little cubicles you go when you want some peace and quiet, then the drawer units, the cupboards, the chairs, the table legs, and finally the pillars, each level adding on the previous. And of course what you see is in the first 2 changes, quite a lot of change to the reverberation times for the various frequencies does indeed occur. But after I hit level 3, not very much happens. And physically, the way we understand that is when you hit a sort of threshold level of scattering. Bear in mind this, again, this situation is one of those acoustic ceilings. Hit the threshold scattering and you've got enough to mix your sound field and start sending stuff into those vertical directions that you kind of miss before. And once your sound field is naturally mixing itself, then not very much after that happens. The acoustic ceiling is being sampled in a realistic sort of a way. So in other words, what you can say is there is really not a huge amount of point in going to complexity level 7, because that's got a lot more surfaces. It's going to take a lot longer to run, but the results are essentially at the same as complexity level 3. So by doing this iterative modeling process, you can find the sort of threshold point where you've got the minimum amount of detail required, and still your results are pretty stable. And once you've got a good compromise, you're ready to go. And what I say to people is find that sort of minimum point where your model is producing reliable results, and do lots of experiments with it. That's the point where you can try out all the kind of acoustic measures to improve things that you might like. And then you'll get a real good understanding of what your situation is. And then at the end, you can think about doing the full model, because I know how it is. If you're doing your report, you want the kind of pretty pictures with the full model and the corresponding results. But the idea is by the time you get around to doing that full model, you'll have a very good grasp of exactly what you want to do with those long runs and how they should behave, how you should set them up. And this means you don't have to waste time doing experiments with a long-running model that may come to nothing. So that's the efficient way to do it. Tied into all this, of course, is the issue of uncertainty in your results, because you saw in the case of that office, even after the results had largely converged, they were fluctuating around a bit. The question is, are those little fluctuations significant? Do you have to worry about them? And the truth is, you do not have to worry about them if they're only moving within your overall uncertainty. And for this reason, to understand what sort of geometrical detail level you need to understand what the uncertainties in your results are. And I confess, I have to sort of beg your indulgence. I kind of move into lecture mode on this one, because back in the days when I worked at the university, I was in the branch of physics, atomic molecular optical physics, and that is the home of the world's most accurate science, including atomic clocks. And these are guys who are doing their error analysis. The error in their results occurs sort of 16, 17 digits after the decimal point. It's quite extraordinary what they do, and they probably spend more time doing error analysis than anything else. So I'm a big fan of carefully checking what the uncertainties in your results are. As one rather strict professor back in the department kept impressing on us all, and I think, well, the truth is, in practice, the world gets by with a slightly looser approach, but strictly speaking, if you have a scientific measurement, a scientific value, or a theoretical value that's based on input from experiment, and you do not quote a plus minus, then effectively the value is of questionable worth, because it's difficult to compare with anything else if you don't know what the uncertainty in that result is. Now, of course, in practice, we're a bit looser, and sometimes we kind of delegate the error analysis and understanding to sort of professional gut feeling or an experience. But yeah, it's a good idea to be as precise as we can. So specifically, it's quite difficult in this line of work to figure out what an absorption coefficient is. The plus minus on that tends to be at least 5%. I don't know if you've seen the round robin they've done with the various labs around the world. It's partially quite depressing. There's a lot of work going on to revise the standards to try and improve these accuracies, but it is hard to do. It really is. And 5% is optimistic for the lower frequencies. If you try and compare room acoustic software with measurements, you will tend to have discrepancies of at least 10%. Sometimes that's partly to do with the approximations in the software, and it's partly to do with measurement issues. But it all adds up to at least 10 plus minus 10%. And I've seen some pretty careful measurement campaigns in my time, and I talk to the guys who do this, and they really sort of go the extra mile. I mean, they're shifting their receiver towers by sort of a few centimeters here and there, just trying to, and they do it at different times of the day, and they're always measuring the temperature and humidity and everything. They're really going the extra mile, and they say it's hard to get below plus minus 0.5 dB. So there's not much point in pursuing 0.1 unless you've got a good reason to, or a very well-controlled system. Don't forget, everything's worse for low frequencies, partly because the wave physics starts to kick in. So these geometrical things start to struggle a bit more, and equally for the measurements have trouble with the low frequencies as well. Don't forget, there are built-in approximations for these geometrical methods. The specific point is, strictly speaking, they're only valid unquestionably for situations where the wavelength represented by a particle is very much smaller than all the other lengths in the problem. In practice, we sort of that gets bent a bit, and you still get useful results, but it's useful to bear in mind what the validity criteria are. Just to give you a little practical example, I thought I'd show you some measurements from the estimable group from Michael Vorländer, the Technical University in Aachen, lead author one, Mr. Brinkman here. These guys really know what they're doing. They've got some serious experience under their belts, and this is just a little round robin of various room acoustic softwares comparing with some measurements they did, and you will see that the discrepancies can very well be on the order of tens of percent. Sometimes you do a little better, especially at the higher frequencies, you can see, but you're very often outside the just noticeable difference. So just to reiterate, we find that the uncertainties in acoustics may well be on the order of a few tens of %. And if you're adding geometrical detail, do keep in mind what the equivalent absorption area of that those additions are. If they're much less than 10% of the total, it's unlikely to do very much. The only exception being, as we've seen, if they make a significant contribution to the scattering. So again, I encourage everyone to do their uncertainty analyses and find out what change is significant and what is not. We can all save ourselves a fair amount of time and work more efficiently doing that. So that was a few practical aspects of sound particles in the field, and so I'll wind up with perhaps some more fun topics. And again, I emphasize, and I'm interested to hear your feedback on these things, because some of these are sort of not our kind of main line of work, and all discussions very welcome. So we do a bit of oralization. I mean, most of the time we're sort of, when we analyze offices, it's like we look at sort of bald numbers in tables and saying, how do they compare with this, that, and the other? Do you fulfill this criteria and so on? But it's nice to hear how your room sounds, of course. It's a nice little feature, so we put it in. And we noticed we had very different priorities from a lot of other people doing oralization, because we're not that interested in music. Well, we are, but just not sort of in terms of the software itself. And we're not really in the virtual reality world either. So those are the kind of two groups who like to do oralization. We're more interested in how well can you understand someone talking in an office, say, with background noise going on. So for this reason, we kind of stuck to monaural. We didn't sort of quite see it being worth it in our case to try and go for binaural. But one thing we did do that was sort of went above and beyond other stuff is we are we'll be developing something, this should be out in the next version, in which you will be able to hear your room combined with your speaker signal and background noise superimposed on top of each other. So you can pretty much hear your speech intelligibility. And our experience is this kind of matches what they approximately say for the numbers quite well. The other thing we've emphasized is the ability to do multiple speakers, which is a useful thing for our sort of customer base. I don't know if you've ever been to one of those theme parks. I mean, I took the kids to Playmobil Land a couple of years back, and you've got this kind of big outdoor sort of campus with all sorts of playgrounds and the like, and it's the whole sort of area is filled with loudspeakers, which come on every 5 minutes and say, will little Johnny please go to the reception where his parents are waiting for him. So it is actually, I don't mean to joke, it's actually very important, but everything is understandable here. But if you have multiple speakers, they can sort of slightly, the signal from one can get in the way of the signal from the other. And so again, this is something that's worth trying to consider, and it's a feature we have added. So in spite of me doing some practice in advance and checking all the settings, I'm afraid I can't do any oral examples for you. Perhaps if people are really interested, we can find a way to get the files to you. But I'm afraid it will just have to be done in terms of slides, what it all sounds like. This is just a kind of a screenshot of what our sort of surface for our oralization looks like. I've got talking in a room full of people. And on the left, that panel there, the orange curve, you can see there, that is that's the RMS value of the speaker signal, which is the thing you want to hear. And the blue is the background noise, all superimposed. You've got in green on the right, you've got the room impulse response. So you can see that the initial sort of a sharp peak is the direct sound, followed by various reflections and the like. But of course, the nice thing, the point I'd like to emphasize here is, in this case, we're doing both signal and noise simultaneously. And if you play that, you can just about understand what's being said. The STI is at 0.54, so you can hear what's being said, but the background chatter is noticeably loud. And the other sort of speciality of our auralization is these multiple speakers. Just for the sake of example, I just did a quick thing with 2 separated speakers, and perhaps if your screen's large enough, you can see this in the top right plot with the green curve, room impulse response. You can see sort of tucked away on the left are a high signal. That's when the nearest speaker hits you, and then about 1.5 sort of 0.15 seconds later, there comes the second speaker in there. And again, I apologize, you can't actually hear it, but when I play this recording, it kind of reminds me very much of the train station. There's that kind of tinny effect with the slight delay on the 2 speakers, so you can understand it, but it's annoying. So quickly dipping into auralization. Incidentally, I have some questions on auralization, which I'd like to put to you in the discussion session. So I'm looking forward to that. But until then, the other sort of exotic topic I promised you was doing sound on the graphics card. If I were doing a live presentation in the sense of actual audience present, I would ask how many of you have heard of graphics cards being used for things other than graphics. It's my experience, it's usually about half the audience. Perhaps that's growing in the technical community, possibly more. But it's worth remembering, the thing about a graphics card is essentially what it's designed to do is to do mathematics on blocks of data at a very high level of parallelization. So if you increase the brightness on your screen, the graphics card is responsible for making sure that all those millions of pixels increase their brightness simultaneously. And of course, going through each pixel one at a time would hardly be the best idea. So these cards are laid out to sort of do big chunky blocks very quickly simultaneously. But of course, there's no reason why you have to calculate brightness and other such things with a card. In the end, you're just processing numbers. And so increasingly in the simulation world, you're seeing more and more use of this kind of hardware. And I think I'm right in saying that the top 10 supercomputers in the world these days are majority GPU. They've got more graphic card technology than they have the central processing unit technology. So it's really where the scientific simulation community is going. And so we wanted to see if this could do anything for us. And we ended up going for the OpenCL platform to help us with that. That's supported by GPUs and CPUs from various vendors out there. I confess that sometimes it's hard to keep track of what's being supported by what, but sometimes you can combine GPUs and CPUs, and sometimes you're not so lucky, but in theory, you've got quite a wide spectrum that you can handle there. So just to give you an example of what might be done, quick example situation, and I'll do some runtime tests for this very simple situation. It's just an acoustically hard hall with a couple of boxes and the like. Fairly simple. I'm just going after sound levels here. And I'm comparing my sort of regular laptop with a so-called entry-level gaming GPU, it's known for about €100, and the custom workstation, which was fitted out with a couple of mid-range GPUs with considerably more memory. And if I run those that simple situation there, the regular laptop can, in theory, give me an acceleration factor of up to 250 times just there, whereas if you go on, the graphics cards are actually really designed for this sort of thing. We have seen speed increases of up to 5,000, which is quite cool. I should point out sound particles are mostly suited for GPU technology, not completely. There's a couple of criteria they don't fulfill, but there is the potential for gain there. Before everyone gets too excited, I must stress that I use that example to kind of flatter the system to a certain extent and show what might be possible. In reality, if you're doing room acoustics, you generally have much heavier memory requirements than that simple situation I showed you there. And the thing about GPUs is they don't like it so much if you're memory heavy. At that point, you have to start making compromises with the parallelization. If you're doing some heavy duty room acoustics, you might not quite see those speed up factors. But my experience is if you're careful with your memory, then you can hope for a decent acceleration using this kind of technology. You just have to watch out if you're doing grid maps or room acoustic parameters with impulse responses, which are very memory heavy and the like. So I'm pretty much done. Just last few thoughts on a final topic, and again, this stuff's kind of up in the air. This is sort of future music here, and all interested acousticians and mathematicians and scientists out there very interested in what you might have to say about this sort of thing. But these sound particle ray tracing type things have long been used indoors because there are certain bits of tricky physics which you have to include outdoors. Up until now, there's not been much use of them outdoors at all. It's been an indoor number, but you can think about doing outdoors. The two key things you've got to put back in if you want to do them outdoors are the meteorological effects. So the weather, basically, the fact that the air temperature and thus the sound speed you're dealing with varies with height above the ground. So you end up with these curved sound paths, and this can be absolutely crucial in environmental noise. I don't know if you've ever noticed sort of in the evening, sometimes when things cool down, suddenly the distant sound sources sound strangely loud. That's due to the temperature inversion, sort of having a warmer air slightly higher in the atmosphere, and that causes the sound parts to curve over and make everything louder. It's a beautiful effect. So there's curved sound paths to worry about because of the weather and the atmosphere, and you've also got interference to worry about. That's another thing, of course. When we threw out wave physics, we ditched interference effects, and certainly for direct sound and indeed so-called ground effects, that's very important for our line of work as well in the environmental noise. So those things are missing. How might we put them in? Well, I just thought, apologies if you don't like your maths. I put this slide in for those who do, because, the curved sound path in the atmosphere, I regard it as a really beautiful mathematical problem, actually. It can be done really, really elegantly with some quite powerful tools, thanks to Messrs. Euler and Lagrange. It's kind of cool, really. I think obviously it's not quite like this, but nature, it almost seems like it knows what the shortest distance between 2 points is, even if that path is a strange one. And if you plug this into these mathematical techniques which are designed to minimize your path length, you'll see these curved paths emerge. If in this case, depending on how your temperature varies, we've got this circular path over the top there. That's what that equation on the right is basically signifying to us. So that's one way you can think about it. You can do some analytical calculations to get your sound paths. Perhaps in a more numerical sense, we might look at just partitioning our atmosphere into sort of various layers, and that have basically much in the same way we did the diffraction, just have the particle deflect as it moves through those layers. But those are the kind of things we're thinking about. In terms of interference, sound particles do have a bit of a problem there. Everything works really nicely if you're just summing energetically. You're not worrying about any phase information or coherent addition of amplitude. So that works fine with sound particles. As soon as you want to put the phase back in and start adding coherently, it gets a bit more troublesome, because you have to start distinguishing between the various particle paths that you've got, and that means a lot of memory storage if you want to do more than a few handfuls of reflections. But we're thinking, you know, maybe you can do direct sound and the floor reflection and maybe a couple of others. Maybe we've just got enough to do that, and that will be a much better approximation than what's come before. So those are the kind of ideas we're kicking around. So that brings me to my conclusions. So that's my content slide replaced with what we've learned. So our sound particles, we call it the SPD method. Don't ask me how that name came about, sound particle diffraction. We just went for the acronym, and I stress we are indeed politically neutral. Even in these busy political days in Germany. Sound particles, SPD, sound particle diffraction, is a ray tracing-like method, as we've seen, because wave physics is a bit tricky at the moment. And we do diffraction using bypass distances, thanks to Professor Uwe Stephenson. And the thing I like about it is it means that your diffraction rules and the rules of the entire simulation stay the same for all times and all places. So it's a proper simulation. In terms of what we learned about doing acoustic modeling, we saw that scattering is a thorny issue, and one that one must treat very carefully. My preferred method is to deal with using iterative modeling combined with a decent uncertainty analysis. And as to the question, do you need to model the chairs? My default answer is no. There may be certain situations where you have to, so don't rule it out, but just check your equivalent absorption areas before you go putting the chairs in, because I've done it in various situations, and typically you can often model an audience area with just a flat scattering sort of absorbing surface, which is tailored to the properties you need, and that works just as well. So in the last section, we had a look at our auralization. We prioritize auralization with background noise and multiple speakers, and that's bearing first fruits for us. We've seen that graphics card acceleration, in our case with the OpenCL platform, can speed things up, especially if you're careful with the memory. Finally, we batted some ideas around about sound particles outdoors, and we noted that we need some curved sound paths and ideally some interference. Perhaps some of us will be able to put our heads together on that one. On that note, I say thank you for listening, and if the audio quality was poor, I apologize. We did do our homework on this one, but as I said, sometimes it just doesn't work out. If you're interested in more, we've done some, we published some papers in various conference proceedings on the matter. But with that, I'll thank you for your attention and look forward to the discussion.